All right, so this is lesson 96. And do you remember how to factor that? Yes, you may. That means you don't remember how to factor that? We called it the difference of two squares. Do you guys remember that terminology? And how you factored something that was the difference of two squares? This was our rule. The difference of two squares was always basically the square root of both of these values. All right, so the square root of x squared is x, the square root of 9 is 3. So the square root of both of these values, and you do a plus over here and a minus over there. Or you could write it in the reverse direction. You could say x minus 3 times x plus 3. You'll get the same thing. So the difference of two squares is always, like if we were to write it like this, if we were to say a squared plus b squared, a squared minus b squared, right? We could say that the difference, that the factor, when you factor that, you get a minus b and a plus b. Just again to show you that it doesn't matter if you put the minus or the plus first. So that's our rule for the difference of two squares. Do you guys remember that now, please? It's like she was about to do that, and then I was like, please, and she's like, maybe I'll show them that maybe I remember it. But that needs to stick with you. That needs to be on your note sheet, all right, for the final. Make sure that you remember that. And so if you remember that that's the case, let's go ahead. Let's say we set this equal to 0. All right, and let's say that I give you this equation here, and I said just like on the last quiz that we just went through, it says solve, which means you're trying to find the values for x, right? How do I find the values for x if that's what this factors to? Well, remember what we do is we set each of these groups of factors equal to 0, right? True? Right? You guys with me so far? And so that means x is going to equal -3, and x is going to equal +3. Right? And so here's the theorem that they're introducing you to, the difference of two squares theorem. It just basically says, if you have the difference of two squares equal to 0, then what will be true is that x will always be, this variable here will always be equal to the positive square root of this perfect square here and the negative square root, right? So x is going to be equal to both 3 and -3. That will always be the case, right? Whatever the square root of this value here is. Now, if you don't remember the theorem, that this is what the theorem says, you could just do what I did right here, and you're going to get the right answers, right? If I give you the problem, I'm just going to give you a problem that looks like this and tell you ask you what's the value of x, and if you do the normal factoring thing that we know how to do with two squares and set them equal to 0 and solve, you're going to get what the theorem tells us is the answer. But you can recognize it the quick way. Like if you saw x squared minus, let's use a different variable. Let's say you saw that m squared minus 25 was equal to 0. Or actually I gave it to you like this. What if I gave it to you like this? M squared equals 25. All right, if I gave you that, you should recognize that that means I can say m squared minus 25 equals 0, and I know that's two squares, the difference of two squares, and so that means m has to be equal to +5 and -5, right? That's my solution for that guy. Does that make sense? That should be pretty easy. We're just doing, it's nothing different from what we've already done. It's really just a shortcut. You see two perfect squares. If you see it written like this or written like this, you should recognize that that means that the variable here equals the plus or minus whatever the square root of that is. Okay, any questions about that? That was my hope was we would go through that one pretty quickly, but we've got time if you want me to walk through another example. Mm-hmm.
Could you do one that would be like a whole lot more difficult?
Well, they're always going to be perfect squares, so they're never going to be super difficult.
Okay.
All right.
So that's about
that's about as complicated as it gets, right? The key to is just that it may be written like this. Probably more likely it's going to be written like that. All right. And so you have to recognize that this is a perfect square here, this is a perfect square here. And so you're thinking, you know, I could give you anything that was a perfect square. 9, this could be a 9, 16, 25, 36, right? All the ones that are perfect squares. So if I said z squared equals 81, you go, oh, it's 2 squares, right? So I know then that z is going to be equal to the positive and negative square root of this. So you could write it, sometimes you'll see it written like that, right? But probably, and by the way, as much as I can, the final is going to be multiple choice. Probably the way the answer is going to be written on the final is that it's going to look like, that was supposed to be curly braces. It's going to look like 9, comma, negative 9. Or it may be in the reverse order, right? Negative 9, 9. All right, make sense? All right, well, let's move on to lesson 97. And this is the Pythagorean theorem. Have you guys seen the Pythagorean theorem before? It's most pre-algebra books will cover this concept, but I want to make sure you know it if you haven't seen it. So, again, this is lesson 97. The Pythagorean theorem it only applies to right triangles, all right? Only valid and so what it says is that if we have a right triangle like this, and we have a special name for this side that's across from that. What's that called? Oh yeah. What's the special name for the side that's across from the right angle in a right triangle? Do you guys remember the special name for that?
Right triangle?
Oh,
This side right here has a special name. Alexa's like, oh, it almost came to me. It rhymes with hypotenuse. Yeah. Hypotenuse, right? This is the hypotenuse. And so the only thing that really matters as far as labeling your right triangle when you're thinking of the Pythagorean theorem is always make the side that is the hypotenuse, make that side C. Okay? And then for the other two sides, it doesn't matter which one you make A and which one you make B. But the Pythagorean theorem says this, that the length of side A squared plus the length of side B squared equals the length of the hypotenuse squared. So the way that we always say that, and the way that I always remember it, is A squared plus B squared equals C squared. So as long as you can remember that C is the length of the hypotenuse, then you'll remember how to use this equation here. And guys, this like never goes away, right? If you haven't seen it before, it's a good time to see it in Algebra 1 because it's just going to keep popping back up. You're going to need it in geometry, Algebra 2. You're going to need it in pre-calculus, calculus. Any math class going forward, you're going to need to know the Pythagorean theorem. All right? So go ahead and commit this to memory. You're going to need it on SAT and ACT, right? It's going to show up on those tests. So it's the length of, the hypotenuse is always your longest side in a right triangle. And so it's basically the two smaller sides. If you square those and add them together, it's going to equal, for a right triangle, it's going to equal the length of the longest side squared. All right? So A squared plus B squared equals C squared. So let's do an actual example of that and make sure that we understand it. So let's say we have a triangle like this. And this is 4, and this is 5, and this is A. All right? So somebody tell me how I would write my Pythagorean theorem based on this triangle.
Wouldn't it be like 5 as C?
Uh-huh. Yep, so we'll put the 5 squared over here on this side.
And then you have A squared and
B is 4, right? A squared plus 4 squared equals 5 squared. Does everybody see that? That makes sense? All right, so let's simplify it. We're trying to solve for a. So this is going to be a squared plus 16 equals 25, right? When I move my 16 over, I get a squared equals 9. Hey, that's that little, that looks just like our difference of two squares things that we did just a minute ago, right? What did we learn in our last example? We learned that this means that a has to be equal to positive 3 or negative 3, right? Another way to think about this, even the book says don't do this. I need to probably look and see why the book says don't do it. They say the square root sign is only, actually here it's fine to do it because they make the note that the square root sign is only designated to, is only used to designate positive square roots. I'll just say in my math career, that wasn't, not all teachers taught it that way. But the point is, can the length of this side be negative 3? Can we have a length that's a negative value? No. So for when you're dealing with physical shapes, physical distances, the negative value, you always throw out the negative value. So really the way that I would encourage you to think about this is that to solve for a here, we take the square root of both sides, all right? And what's the square root of a squared? A. And what's the square root of 9? 3, right? So that's our value for a. It's 3. All right, and so we use the Pythagorean theorem to figure that out. Now, this is really cool. It may not seem too cool, but here's the thing. Let's say I'm standing on the ground and I'm looking at a pine tree, and you know, everybody knows that this is what pine trees look like, right? Does that look just like the pine trees in your yard? Me too, right? And so I'm standing from the base of this pine tree way over here. And I have a tool that will tell me that the angle from me to the top of this pine tree is, let's say that it tells me that that angle is 30 degrees. All right? And so if I know that the distance, say, from where I am to the base of the pine tree is 25 feet, I can use something that's kind of based on the Pythagorean theorem and the trig functions the conclusions that we draw from this. I'm not going to go into the trig functions, but it's like this type of stuff allows me to figure out, based on just this information right here, it lets me figure out what the height of this tree is. All right, so this is like real world practical stuff if you learn it. It'll help you be able to solve, like if you're a carpenter, there's certain things that you can do, like if you're trying to build a door that's square, and you think about having a line through here, you can use the Pythagorean theorem to build this piece that's this length here, based on what the length of these sides here are. Like if this is 4 feet and this is 5 feet, then you can figure out what the length of this guy needs to be using the Pythagorean theorem, and then you can ensure that the rest of it's actually square. Because you want to have right angles in all these places here. So there's real world applications to this. So this is one of those places that's kind of easy. You know, students always ask, why do I need to know this? Right? This is actually something that has a kind of easy to see the real world application. So this is a very, very important theorem, and I want to make sure that you guys don't get out of this class without having seen it. But do you guys see how easy it is to plug in the values into the Pythagorean theorem to figure that out? By the way, that was a special triangle. That's kind of just one you need to remember, what we call the 3, 4, 5 triangle. 3, 4, 5 right triangle. If you ever see, like if you see that these sides are 3 and 4, the smallest sides are 3 and 4, you just automatically know, if I use the Pythagorean theorem, this is going to be 5. All right? Or if I see that it's a right triangle and the longest side is 5 and another side's 3, I know if I use the Pythagorean theorem, I'm going to get a 4 right here, right? It's just that one of those, the numbers work out like that. So this is kind of a good triangle just to commit to memory, the 3, 4, 5 triangle. So that if you see it on a standardized test, you just know immediately that's the length of the other side. And the reason that's the length of the other side is because that's what fits the Pythagorean theorem. All right, let's do one more of these guys, just so that because it is so important, and I don't want you to not be able to do these. This one's a little more complicated, but if you understand how to use the theorem, it's not hard. So we have this right triangle, and we have this value here is the square root of 61. This value is k, and this value is 5. All right? So remember, again, my Pythagorean theorem says a squared plus b squared equals c squared. Always identify c first. Okay? Because c is the one thing that you have to get right in these right triangles. Which value on this right triangle is c?
61 squared.
61 squared, right? C is always the longest side. It's always the side that's opposite the right triangle, the right angle, sorry. So square root of 61 has to go right here. All right? These other two, it doesn't matter where you put the other two, but this one's the one that matters. So we'll just say k squared is going to be our a squared, and then plus 5 squared is going to be our b squared. All right? Now, let's simplify. K, that means k squared plus 25 equals what's square root of 61 squared?
61.
It's just 61, right? Squares just undo square roots and vice versa. Square root of a squared equals a, just like the square root of a squared also equals a, right? But square roots just undo squares and vice versa. So this is just 61. And so we move our 25 over and we get that k squared equals 61 minus 25 is 36. You guys check my math on that. Does that look right? 61 minus 20 is 41. Minus 6 would be, oh wait a minute, minus 5, yeah, would be 36. That's good because that's a perfect square, right? So now we take the square root of both sides. And when we do that, we get k is equal to 6. Any questions about that? Yes?
Is the whole point of these just finding the missing side?
That's right. Yep. Yeah. The Pythagorean theorem allows us to find the third side for a right triangle if we have two of the other sides. Okay? All right, let's move on to lesson 98. Lesson 98, we're trying to find the distance between 2 points, and they also give us the slope formula. Now, I think we've talked about the slope formula before, but maybe not. I don't remember. So let's say we have a line like this, and let's just say that that line, we know that it goes through the point 2, 1, and it also goes through the point 1, 2, 5, 2. All right, so we've got a line. We've got this line right here. So this is 1, 2, 3, 4, 5, 6. This is our x-axis. This is 1, 2. That's actually 3, 5, 3. Okay. 4. This is our y-axis. So here's our line, right? I'm only just going to draw that small portion there. I'm trying to draw a little straighter, if I can. The line goes through that, and we want to find what the distance is between these 2 points. Okay? So how would we do that? Well, it turns out that what we just learned, the Pythagorean theorem, is exactly how you would do that. Because, think about it. If I take this line and I draw a dotted line down here, and I draw another dotted line down here, what did that just form? It just formed a right triangle, right? And I don't know what the length of this distance is, but do I know what the length of this is? That's really easy for us to see, right? I just count over from here and I go 1, 2, 3, so the length of this guy is 3, right? And I count up from here, I see the length of this guy is 2. So I have a right triangle, and the unknown that I'm trying to find, this distance here, is our C in our right triangle. Does everybody see that? So if I want to know what the distance is between those 2 points, I can just do a squared plus b squared equals c squared. And so my a squared is 3 squared. My b squared is 2 squared equals c squared. And so 9 plus 4 equals c squared. That's 13 equals c squared. And so that means that my distance, that's c, is basically square root of 13. Now I could punch that in my calculator if I wanted to, and I could get an actual decimal value of that for that. But that would be sufficient for this. We could say the length of that line segment is 13.
So if you ever switch out A and B, does it matter?
It doesn't matter, right? They don't matter. Now, this is the way that I could do it if it's easy for me to count, all right? Let's say we know these 2 points, though. Or we are going to know these 2 points. So what is this point right here on my coordinate plane? This point right here is the point 5, 3. Right? You guys see that? You got to know how to graph your points, right? But if you know how to graph your points, you know that that's 5, 3. And then what's this point right here? Yep.
2, 1.
2, 1, right? Those are my x and y values for both of those points. Now, how do I, if I don't want to actually like count on my number line, right? Or let's say, count on my graph. Or let's say I'm not even given a graph. Let's just say I'm given a couple of points and asked to find the distance. How can I mathematically figure out what this 3 is right here? Sorry, I'll get it right in a second. Using the points that I've been given, how can I mathematically figure out this distance here that we said was 3? Isn't it just the value of this x minus the value of this x? Isn't it just the 5 minus 2? Do you guys see that? It's 5 minus 2 is what gives us 3. That's how we got 3. We counted over. We went from the 2 and went over to 5. But if I want to find that distance, I take the 5 and I subtract the 2 from it, right? If I want to find this distance 2 here, mathematically, we counted up. We went from 1 up to 3. But I find that mathematically by taking my y value here and subtracting from it this y value, right? And I get 2. And so what that tells us is that I could think of my a squared here, which we said was 3. I could think of that if I generically name these points x2 and x1. I'm sorry, x2 and y1, and generically name this. I'll get it right in a second. Sorry, guys. x2, y2. This is my second point. And this is my first point, x1, y1. All right? I could say that a then is actually the difference in the x values. So x2 minus x1, right? That was our 5 minus 2, right? Square that. Plus, my b is the value of the y coordinate minus this y coordinate. So y2 minus y1. Square that. That's got to equal this distance c here, right? That equals c squared. And so from that, if I just want to write down a formula that says c is equal to something, I could say c is equal to the square root, right? If I want to get rid of this square here, I take the square root of both sides. I could say c is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. And that is a formula that I can use to always find the distance between 2 points. All right. Usually the way you see the formula written is instead of using c, even though it represents the hypotenuse on our right angle, since we're trying to find a distance, they usually write it as d. And so we call this right here the distance formula. All right. So what that means is now I have a formula that I could give you any 2 points on a coordinate plane and ask you what's the distance between those 2 points, and you could just plug in the values to this and you could find what the distance is. All right. I worked it out like this first because I wanted you guys to understand The reason this works is because the Pythagorean theorem is true. All right, this is totally based on the Pythagorean theorem. And so if you understand the Pythagorean theorem, you could remember the formula just based on that. Now, I'm giving you guys a note card for the final. My recommendation for the final, write this down, right? Because you're going to see a problem that's something like, I'm going to say, what's the distance between the points 3, -1, and, I don't know, -2, 5? All right, what are the distance between those points? And you can just plug it in that formula and figure that out. Yep.
What size does the note card have to be?
That's an 8.5 by 11 sheet of paper. So whole piece of notebook paper, writing on one side. Okay? So let's see if we can find the distance between this right here, these 2 points, based on that formula. All right? So I'm going to rewrite our formula down. D equals the square root of x2 minus x1 squared plus y2 minus y1 squared. And so that means D is going to be equal to the square root of, this is my x1, this is my y1, this is my x2, this is my y2. So what am I plugging in right here? x2 minus x1 is going to be -2 minus 3. I'm just plugging those values in. Squared, right? Plus, what's y2? 5. Minus, what's y1? -1. I would encourage you to put the minus and put parentheses here so that you make sure you don't mess up your signs. All right?
Can't you just make it a positive one?
You can, but I would recommend doing this first, plugging it in like that so you don't accidentally mess it up in your head, right? If you're comfortable with doing that, yeah, it's technically 5 plus 1, right? So I'm going to do that math when I do my next step. So I'm going to do -2 minus 3, that's -5. So I've got a -5 squared here. And so like Jonah said, this is 5 minus a -1, which is really 5 plus 1. So this is a 6 squared, right? And so now I've got the square root of 25 plus 36. That is 61. So the square root of 61. 61 is a prime number. You're not going to be able to factor that any further, so that would be our answer for the distance, just the square root of 61. Okay? So make sure you know the distance formula. Any questions about using that? All right, the other thing that kind of comes out of this drawing here is the value for the slope, how we calculate the slope if we're given 2 points. What is so what's our equation for a line that's in slope-intercept form? You remember that? Y equals what? This should be on your note card, your note sheet, so you don't forget this. Y equals mx plus b. Okay? And what do these values m and b represent? What's m? Anybody remember? No one remembers? This is why so many of you guys left the first problem on your quiz blank, because you had to remember slope-intercept form. This is your slope, and this is your y-intercept. So this tells me where my line crosses the y-axis. This tells me the slope of that line, basically the angle of the line. Okay? And so do you guys remember like a shorthand way that I said remember what slope is? Slope is something over something. What was it?
Rise over run.
Slope is rise over run. Who said that? Cohen, okay. So slope, elm is rise over run. Slope equals elm. And that equals rise over run. So I just want you to see again the way that I've drawn this with a right triangle. What is our rise for this line here? Our rise is this distance 2, right? And how do we find that distance 2? Well, the same way we did it in our distance formula. Our distance for the rise is y2 minus y1, right? The run is this distance 3 right here, and so run is going to be x2 minus x1. So the distance formula and the slope formula are kind of related because they both have this x2 minus x1 and y2 minus y1 in it, right? So as long as you understand what that means, then I could also give you 2 points and say give me the slope for it. And so if I asked you for the slope of a line that goes through these 2 points, we would say, well, that is y2 is 5 minus y1, which is -1, and x2 is -2 minus 3. And so I would say that that this value here is 6 over -5, and so I would just write that as -6/5. That would be my slope if I asked you to give me the slope for a line that goes through those 2 points. Make sense? Again, it's just a formula, right? Just make sure you know that formula. But I remember rise over run, and rise over run helps me remember the formula. Because I know that rise is the difference along my y-axis, and run is my distance, the difference between the x values. It's the distance on the x-axis. All right, any questions about using these 2 formulas? Are these going to be on your note sheet? Yeah, better be on there. Lillian, I got this. Need it on the note sheet. Who needs a note sheet? All right, let's move on to the next chapter that I want to cover, which is 100. All right. This is so easy. I think you guys already know it, but I just want to make sure you know it. And it's just one of those that's so easy. I'm like, there's no way I'm going to let you get out of my Algebra 1 class and not still know how to do this. If you're still confused about rounding, let's make sure we get that down, right? So if I told you to round this number here to the tens place, what would you tell me the answer would be? Yes?
970.
970, right? Now we got to know what the tens place is. We have to know that this is the ones place. Whoops. This is the ones. This is the tens. Right? This is the hundreds place. Right? And just write down, we might just say that as ones. We say that as tens. And then say this as hundreds. Right? So if I said round that to the tens place, it means we want to round to this number here. And so we say that that equals 970. If I said round it to the hundreds place, you would say it's 1,000. Right? Because we're rounding now to this place. And how did Jonah know to round, when we said go to the tens place, how did he know to round that 6 up? Yes?
Use the 5.
Yeah, you always look at the number that's immediately after the place that you're rounding to, right? So if this number here is 5 or greater, then you round this number up. If this number here is less than 5, then you round it down. So if the number I had told you to do was 964, and I said round it to the tens place, you would have said the answer is 960. Did I say 74? I meant to say 64. 964. Okay? So this one rounds to 960. This one here rounds to 970. I should really write squigglies. But this is rounded to the tens place. Now, let's talk about decimals. All right? And with decimals, so, this keeps going. We have the ones, the tens, the hundreds, the thousands, the 10,000s, right? But what about when we're talking about decimals? So if I have a number like 96.52396, for example, all right? What do we call this place right here? Does anybody know? Yep.
The 1/10.
The tenths, yeah. So you'll sometimes see it as 1/10. This would be the 100ths, and you always have the THs on these, right? Hundredths. You don't have THs on these ones, tens, hundreds, but you have THs whenever they list those there. So there's like a little table Do they write it out? Let's see here. You don't always see the one part. That's why I was trying to make sure they didn't do that in the book. You'll often just see it like that, right? So if you see tenths with the THS on the end, you know you're talking about after the decimal place. When you see tens with no TH or just 10, you know you're talking about to the left of the decimal place. Okay? So if I asked you to round this guy to the thousandths place, all right? Round to thousandths with the THS on the end, where would you, oh, there's actually a D in there, I'm sorry. It's DTHS, hundredths. And this is DTHS right there. If I said round that to the thousandths place, what number am I talking about? Which number after the decimal is in the thousandths place? Yes.
3.
The 3 is, right? This is the tenths, the hundredths, this is the thousandths. And so if I'm rounding to this point, what does that value round to? Am I moving the 3 up or down? Remember, I'm always looking at the next number afterwards to figure out if it goes up or down.
Up.
So it goes up, right? Because this number is 5 or greater. So this rounds to 96.524. All right, does everybody see that? Now, another way that I might tell you to do it, and this is more often, yes?
Would you keep the zeros on the end or?
I would not. I would just write it like that. I won't count it wrong if you put zeros on the end. But remember, this is going to be a multiple choice test, so this is probably how it's going to be listed on the test. All right. Most often, you're not told to round it to the tenths or the hundredths or the thousandths. They'll say round it to 4 decimal places, right? Or round it to 2 decimal places or something like that. So what if I had the same number here and I told you round it to 2 decimal places? Now, which number am I interested? Is it going to end with? It's going to end with the 2, right? 2 decimal places. And so what is this going to be rounded to 2 decimal places? 96.5, 2, right? Because this number here that comes immediately after it is less than 5. All right, so these are rounding rules that you've learned before, but I mean, sometimes some of us, we miss something the first time around, right? We never really got it down well, but I want to make sure you've got this down now. So does everybody understand how this works? Any questions about it? Like I said, this is how you'll probably see me write it on the test, on the final. I'll say this many decimal places and to just make sure that you can do that, okay? Yep.
I don't even know why I'm confused about this, but on this one, you just rounded it. You left it alone, which is what I've been taught. Is if it's less than 5,
That's right.
leave it alone. But on that one, you rounded it down.
Oh, okay. And that's because you leave it alone if it's after the decimal. But if it's before the decimal, we left it alone where we were rounding to, but you have to change all these guys to 0, because this number here, if we just left it alone right there, 96 is not near 964, right? So that's why you have to add zeros whatever numbers you're dropping when it's in front of the decimal place. Does that make sense?
Yeah.
Okay. Good question.